Hello, my name is Paul Craig, and I'm part of the team that's presenting the Python for Chem Informatics Driven Molecular Docking on May 1st. In preparation for this event, I've prepared a series of brief videos to help people who are new to Python coding or who haven't done it for a while to get used to what's happening. And what's actually happening in these preparatory videos is I'm slowly going through the materials that I'll move through more quickly in the first hour of the crash course on May 1. So with that said, we're going to go back to our preparation uh, preparation guide. And in this preparation guide, we have links for a series of notebooks. This is to help, once again, people who aren't experienced or haven't used Python for quite a while. The previous video covered Python basics. In this one, we're just going to start looking at molecule representation. So to use this, we just click on this link and bring up another Colab notebook. Once again, this is from the Molecular Sciences Software Institute, and it was prepared, Jessica Nash prepared this. And so in this unit, we're looking at how we represent molecules digitally. How can a computer understand molecules? All right. And some questions. How are molecules represented on computers? What is a SMILE string? And what are common molecular file formats? And so our objective here is to learn to convert molecules from chemical formulas and structures into SMILE strings. And those aren't the only formats that we'll see for molecules. But in this chem informatics course, we're going to be focusing mostly on using molecules as SMILE strings. Now, some of you have already used situations where we use strings to represent biological molecules. So, for example, if you're looking at DNA, what I have in this screen is this is a portion of the DNA sequence for an enzyme called human dihydrofolate reductase. Okay, so this is an enzyme in nucleotide metabolism, and you can see we represent, we have A, T, G, and C in here as the nucleotides. Now, this is a string that represents the DNA. And you may have done blast searches with DNA strings or protein strings. And so a string is much easier for a computer to work with than a three-dimensional structure. And so that's why we use strings. It's a much more rapid calculation, and often it carries enough energy, enough information for us to do the job. Or perhaps you've also looked at proteins and used protein strings to do blast protein searches or other kinds of PFAM or different sequence alignments. Okay, and each of these letters represents an amino acid. Now there's 20 amino acids that are commonly found in protein. So if you look in this string, you're probably going to find all 20 of those amino acids, or at least most of them. All right, so that's nucleic acids and proteins. Well, when we move into chem informatics, we're working with molecules, small molecules. For example, the molecule that's shown here is aspirin. All right, and so with aspirin, we see aspirin has an aromatic ring. It's got an acid function here. It's got an ester function here. How do we represent that in a computer as a string? Well, there are a number of options. One of those options is called a SMILE string, and that's what we're going to be focused on in this exercise. There's a couple others. One's called an inchy key, another one's called inchy. And so those are different ones. I have not worked with those, so I can't tell you much about those, but we will take a look at some of the coding that's involved with SMILE strings. So SMILES stands for Simplified Molecular Input Line Entry System. Okay, and so this is a way to represent a molecule, a 2D or 3D molecule, as a list of characters. And so in SMILE strings, first of all, we don't typically show the hydrogens when they're bound to carbons. We might show them when they're bound to oxygens or nitrogens or other things, but not when they're bound to carbons. So this is SMILE strings in the way they're visualized reflects the way we typically do line drawing for organic chemistry. All right. So the SMILE string for this molecule, which is ethanol, there's a carbon here and a carbon here, and then an OH group here. Now, each of those carbons also has enough hydrogens to saturate it, but the way we represent this molecule is a SMILE string CCO. Now, there's a link in this page to a tutorial that tells a lot more about smile strings that you can learn. But to be honest, in this exercise and in the crash course, we'll be recognizing smile strings a little bit, constructing a few just to get a feeling for it. But most of the time, we'll pull the smile strings from sites like PubChem. All right. So SMILES actually supports all the elements in the periodic table, and atoms are represented as a single capital letter, or if it's a two-letter element, like thorium would be capital T, small h. All right, and also typically we use uppercase letters to refer to non-aromatic atoms, and lowercase letters refer to aromatic atoms. We'll see this later. In terms of bonds, a single bond is represented by a dash. Usually those are just implied, so we don't include those unless there's some clear reason to do so. An equal sign tells us it's a double bond. A pound sign tells us it's a triple bond. This is in a SMILE string. An asterisk indicates an aromatic bond, and a dot indicates two disconnected structures. And we'll see examples of this as we work through these notebooks. All right? And so if we, single bonds, as I said, are the default. So if you type in CC, that would mean two non-aromatic carbons attached to each other. We can represent branches using parentheses. So for example, if we had CC and then a parentheses with an O inside and then a C, that's 2-propanol. CC with a double bond O would be 2-propanone. So that's how we represent branches. Once again, this is a very simple explanation of SMILES. There's a lot more depth to this. And then finally, we represent rings by we have the first element in the ring. We give it a number. So C1, CCCC1. Okay, so that's cyclopentane. There's actually five carbons there. And it tells us that C1, the C1 here connects to the other C1. Pyridine here is shown as N1. Notice these are all lowercase. And so N1 connects to C1 to form an aromatic ring. So here's a couple examples of SMILE strings. So here's 2-propanol. And so the SMILE string for 2-propanol is CC and then the parentheses O, close parentheses C. And here's the formula for 2-propanol, or the chemical structure of 2-propanol. And if we look at the structure breakdown, that first C refers to a carbon atom, which is shown right here. The second C is also a carbon atom, shown right here. There's a parentheses with an oxygen, so that oxygen is a branch off that carbon atom. And with the oxygen, the hydrogen is shown explicitly. And finally, we end with another carbon atom, which ends right here. So our actual formula is C3H8O, but what we see here are the 3 carbons and the oxygen. A little more complex structure. The SMILE string for ethyl acetate is shown here. So C, C, O, C, in parentheses, equal sign O, close parentheses, C. So this one actually goes from right to left. So the first C is a carbon atom. That's right over here. The second C is a carbon atom. That's right here. Then the third atom here is an oxygen, but it's just an oxygen in line with the carbons. It's not a branch. Then it goes to the next element, which is a carbon atom. So here's our 4th carbon right here. Then we have a branch off that 4th carbon. It's a double bonded oxygen, or a carbonyl oxygen. So that's this oxygen here. And then we end with another carbon here. So that's just an explanation of the SMILES string for ethyl acetate. And so we have an exercise here. And for this exercise, I'd like you to take a few minutes to come up with a SMILES string for different molecules. And the box here is actually an executable. It indicates an executable cell. Pardon me. But it's really just a list. Every line is commented, so it's really just going to be a series of comments. So I'm hoping you took a couple minutes to work through this, and we're just going to put the answers in. So the SMILES string for ethanol is CCO. I think we actually had this up above. Okay. Now the SMILES string for water. This is interesting. We don't list hydrogens in SMILES strings. So the SMILES string for water is just an O. All right. The SMILES string for benzene. I've seen several different ways to represent this, but the way that I do it is lowercase c1, so that's our first carbon, then carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6, we put a 1 on that one. So that's going to be benzene. Our next case It asks us what molecule is represented by the SMILE string O equals C equals O. Well, that's going to be carbon dioxide. Okay, the next question is, what's the SMILE string for an amide group? Now, an amide group is a C double bond O NH2. And so what we do there is we have a C uppercase, and it's got a double bond O, so an O branch off it in a double bond. So we put a parentheses, an equal sign, and an O, and close the parentheses, and then we put an N. Now notice we don't put the hydrogen in the SMILE string. SMILE strings don't require hydrogens. SMILEs, the programs are written to interpret that. So now the next one is asks us for a four-membered carbon chain with an amide group on the second carbon. All right. So we've actually got so we've got our first two carbons. So there's carbon 1, carbon 2. Now we've got an amide group off the second carbon. So it's going to be C double bond O and H2. So it's a branch. So we start off with that to parentheses tell us it's a branch. And we put a carbon. Now that carbon, this carbon's going to have bound to it a double bonded oxygen and a nitrogen. So the double bonded oxygen is another branch. So we put another parentheses, an equal sign, and an oxygen. Then we come out of that parentheses, and we have a nitrogen. So now here is our C double bond O N. That's our amide branch. Okay. And we need to finish that off with two more carbons. So that's our, those are our strings. And we'll actually, in the next workbook, we'll actually go through and build some of these. Or actually, not just build them, but we'll display them using a tool called RDKit. Now, there are a number of molecular file formats out there, and I'm not going to read through this whole document or this whole table for you, but just to say SMILE string is one that we just used. There's also something called INCHI for International Chemical Identifier. MOL or SDF, those are structure files. They can have two-dimensional or three-dimensional coordinates. PDB stands for Protein Data Bank. And that contains the coordinates for proteins or for any molecule, actually, three-dimensional coordinates, but it also has a lot of room for additional information. XYZ, those are files that simply contain three-dimensional coordinates. CIF, it would be a text file format that contains crystal structure data. PQR is a new version or another version of a PDB format that includes partial charges and radii on molecules. PDB-QT is one that includes a PDB format that adds the torsion angles and charges used in autodock. It also adds hydrogens to a structure. And MOL2 is another atomic coordinates format. So that's the end of this second notebook. So I'd encourage you to take a few minutes to think about what you've learned here before launching into the next one, and maybe even take a break for a while. This is a lot of information, especially if you haven't used Python before.